Okay, welcome again. In the last class, we were discussing about this Wiener filter. So the problem statement in the Wiener filter was that given an input sequence un or xn to a discrete time linear time invariant filter having some filter weights w0, w1, w2 and so on, you find the output yn and then you have a desired response dn and you estimate the error sequence en, which is dn minus yn, and the problem was to find the set of filter weights in such a way so that this error is minimized in some statistical sense, or we minimize this mean square error. So we have defined a cost function j, and then we have seen that since j is a function of the filter weight, so we have applied a gradient operator on j, and that gradient vector was equated to 0. So from that we have got an important conclusion, which is the principle of orthogonality, and which states that E of u of n minus k into en star, it is 0. Okay, it means for this Wiener filter to operate in the optimum condition, or to find the minimum value of the mean square error, the input sequence and this estimation error, they must be orthogonal to each other. Okay, so using this principle of orthogonality, we will derive a set of equations which is called as Wiener-Hopf equations, which gives you a solution for this Wiener filter. Okay, Wiener-Hopf equations. So we start from this principle of orthogonality, that u of n minus k into en star is equal to 0. Okay, and this en was the error sequence, which is dn minus yn, and this yn is the response of the filter, which was expressed as a linear combination of filter weights with the input sequence. So in general, we assume that the filter is having infinite impulse response or the filter coefficients, they are infinite in length, but later on we will fix this condition to a finite impulse response. Okay, so if this is en, what will be en star? It will be dn star, the conjugate of dn minus k from 0 to infinity, and wk into u of n minus k star. Okay, this is n conjugate. So if I put this n conjugate here in this equation, what I will get, this equation will become expectation of u of n minus k, and since we have already used a variable k here, and again we are using k here, we will use a different variable here. Suppose I use, in place of k, I use I, so I can write it as dn star minus I from 0 to infinity wi into u of n minus I star, or in fact I write woi, O for the optimum filters. Okay, because when this condition is satisfied, when this principle of orthogonality is applied, it means the filter is operating in the optimum condition. It means at that point we have obtained the minimum value of the mean square error. So these weights in that case will be the optimum filter weights. So O is just for optimum. Okay, so in place of this en star, now you can replace this with this equation, that is dn star minus summation from or I from 0 to infinity woi into u of n minus I star equals 0. Okay, so if you expand this equation, you can have E of u of n minus k into dn star as one term. Another term will be minus e of summation of I from 0 to infinity woi u of n minus k into u of n minus I star equal to 0. Okay, so this term u of n minus k is now multiplied with this part. So, or you can write it as e of u of n minus k into dn star is equal to, if you take this expectation operator inside the summation, so you can write it as I from 0 to infinity woi e of un minus k into un minus I conjugate. Okay, so if you rearrange these equations, write this equation on the left hand side, I can write it as I from 0 to infinity woi e of un minus k into u of n minus I conjugate is equal to e of un minus k into dn star. Okay, so if you interpret now this equation, what this equation is, so you have now a set of equations which is summation of I from 0 to infinity woi, it was e of un minus k into un minus conjugate is equal to e of un minus k into dn conjugate. Okay, now if you look to this term, e of expected value of u of n minus k into u of n minus I star, what will be this? See, this is the autocorrelation function. Okay, this is the autocorrelation of this random sequence un, but at what lag? When you define the autocorrelation at a lag of k between sequence un, so you define it as u of n minus k into u of, sorry, it will be, we define rk as expectation of u of n into u of n minus k star. Okay, this is called as the autocorrelation at a lag k. So it means one sequence it has n sample, so another is delayed by k sample. Okay, so this k is basically what? This k is basically this n minus k, n minus this n minus of n minus k. So you get n minus n plus k, you get k. Okay, so in this case, since both are u, the only difference is in one case you have n minus k, in one case you have n minus I. So this is the autocorrelation, but the lag will not be k. So at what lag it will be the correlation? So that will be n minus k minus n minus I. Okay, so it will be n minus k minus n plus I, or it will be equal to I minus k. So this is the autocorrelation of this sequence un, input sequence, at a lag of I minus k. And similarly, this right hand side equation, e of u of n minus k into dn star, now this is the cross correlation. Okay, because we have two different sequences, one is un, one is desired response dn. So what is the lag here? In this case, the lag is n minus k minus n, which is minus k. So this is the cross correlation sequence between u and d at a lag of minus k. So suppose I denote it with p minus k. Okay, so one term is your autocorrelation between the input samples. The right hand side, this is the cross correlation between the input and the desired response. So this equation can be written as now summation of I over 0 to infinity WOI Ri minus k is equal to P of minus k. Okay, so where k is 0, 1 and so on. So this is a set of basically or a system of equations. Solve these equations, you can find a solution for Wi, which gives you the optimum filter, and these equations are called as Wiener Hopf equations. Okay, so this is Wiener Hopf equations. Okay, now these equations you can expand in the matrix form, you will get more insight into this. So I have a set of equations I from 0 to infinity WOI Ri minus k is equal to P of minus k, k from 0 to infinity. Okay, so this is the situation when we assume that the impulse response or the filter coefficients I varies from 0 to infinity. It means we have infinite filter coefficients. But see, practically the filter coefficients has to be finite. Okay, so practically if you want to implement this using the linear convolution, then these filter coefficients must be finite in length. So let us assume that we have only m filter weights. Okay, in that case, so for finite filter response, if the impulse response of the filter is finite, in that case your I will go from 0 to m minus 1 only m coefficients are there, and WOI R of I minus k will be equal to P of minus k. Okay, so k is 0, 1 up to m minus 1 in this case. So if you expand these equations, you will set that you have a set of linear equations, nothing else. Okay, for k is equal to 0, you see for k is equal to 0, what you will get? The first equation that you will get, if k is 0 in this here and k is 0, and then I varies from 0 to minus 1, what you will get? You will get WO when I is 0, WO is 0 into R of 0 plus WO1 into R of 1, because k is 0, now I is 1. The next case, WO2 into R of 2, k is 0, I will become 2 and so on. Last will be your WO of m minus 1 into R of m minus 1 is equal to P of 0. So you'll get one linear equation. Okay. Then when k is equal to 1, again in this terminal k is set to 1, in this factor again k is set to 1, and I will again vary from 0 to m minus 1. So you will again get W 0 0 R of, now this will be k is 1, I is 0, you will get R of minus 1. Then plus WO1 R of 0 plus WO2 R of 1 and so on, WOM minus 1 R of, you will get now minus 2, because k is now 1, k is 1 and I is m minus 1, so it will become m minus 2 is equal to P of minus 1, and similarly so on. So when k is m minus 1, you will get WO0 R of, now k is m minus 1, I is 0 here, so you will get 0 minus of m minus 1, you will get minus m plus 1 and so on, and last will be WO m minus 1, last will become R0 is equal to P of minus m plus 1. Okay, this is mth equation now. So you have basically a set of linear equations with m linear equations with m variables. What are the variables? The variables are these filter weights WO1, W0, W1, W2 up to W1 minus 1. So if R0, R1, R2, Rm minus 1 is given to you, and P0, P minus 1, Pm minus 1, M plus 1 is given to you. So you can solve this set of linear equations. We can find a solution for these filter weights. Okay. So in more compact form, you can write these set of n linear equations in the form of a matrix. So on the right hand side, you have a column vector of cross correlations, that is P0, P1 minus 1 up to P of minus M plus 1. This is a M cross 1 vector. On the left side, you will have a multiplication of a matrix which is of M cross one side, M cross M, with a M cross 1 vector, isn't it? So this M cross 1 vector will be now a vector of the filter weights. So we have W O0, WO1, WO2 up to WO M minus 1. These are filter weights. And this M cross M matrix will be a autocorrelation matrix. So its first element will be R0, then R1 up to R of M minus 1, first row. The second row will be R of minus 1, then R of 0, and so on. So last will be R of minus M plus 1, and so on, R 0. So if we denote this matrix with R and this matrix with W, or W optimum, or WO, and this matrix with P, so these equations can be written like R WO is equal to P. Okay, where R is a M cross M autocorrelation matrix, W is a column vector of the filter weights, and P is a column vector of the correlation coefficients. Okay, so if R is non-singular, that is, if its determinant is non-zero, you can find W optimum as R inverse P. So this is what is my Wiener filter solution, or what is the Wiener-Hopf equations for a filter which has finite impulse response. What you have to just find, you have to find R, that is the correlation matrix for the input sequence, and P, which is the correlation vector for the between your input and the desired response. So once you find these two matrices, you can find the inverse of R and multiply with P. You can find a column matrix for WO, which will contain the optimum filter weights. Okay, so this correlation matrix that we have defined here. So in the previous classes, we have seen that how we basically compute this R. It is given by the E of U of n into UH of n. So H of n is the Hermitian transpose of UN. Okay, and U of n itself is a column vector. So U of n is a column vector. U of n minus 1 up to U of n minus m plus 1. M samples of the input sequence. So this is M cross 1 vector. So to multiply this with its Hermitian transpose means that you have to take its transpose. So columns will be converted to rows, and then you have to take conjugate of each. Okay, and then you take its expectation. So you multiply first, this is now a 1 cross M vector. So UN into UN star its conjugate and its expectation, you will get autocorrelation at 0 lag. It will become R0. Okay, then un into u of n minus 1 star and its expectation. You will get correlation at a lag of 1. n minus 1 to become 1. Similarly, r of 2 up to so on, r of m minus 1. Okay. So then you multiply u of n minus with u of n, you will get correlation at a lag of minus 1. Then correlation at a lag of 0 and so on. Okay. So last will be r of minus m plus 1 and this will be r of 0. This is how you define the correlation matrix. Okay. It is the expected value of un and its Hermitian transpose, where un is a column vector of the input samples, m samples, right? And this matrix, we have seen that this matrix has some properties, beautiful properties, that it is Hermitian. It is a Hermitian matrix. Hermitian matrix means R H is equal to R. If you take its Hermitian transpose, it will be equal to again the same matrix. And that is because of this, we have seen one property of the autocorrelation that R minus K star is nothing but equal to RK. So if you take the Hermitian transpose of this matrix, so rows will be converted to columns. So R of 1 will come here and this will go here. And then you have to take conjugate of each other. Okay. So if you take the conjugate of R minus 1, it will become R1. Okay. So it will be same. Another property of this matrix was it is Topless matrix. So this autocorrelation matrix is Hermitian matrix as well as a Topless matrix. Topless matrix means all the diagonal elements they are same, and all the elements across another diagonals they are also same. Okay, parallel to the main diagonal they are also same. This is for R0, it will become here R1, then R2 and so on. So these elements are same, this diagonal is also same, this diagonal is also same, and so on. This is what is called as a Topless matrix. Okay. And similarly P, which is the correlation between the input and the desired response, we can also express this P as expectation of u of n into dn star. Okay, which will give you a matrix of P0, P minus 1 up to P of minus n plus 1. Okay. Mind it that when you have to find this correlation matrix using this u of n, of course it is a vector, and this dn is not a vector now, because now u of n will be n cross, let us suppose it is m cross 1 matrix of the input samples, that is u of n minus 1 and so on, and this d of n is a single element, it's not a matrix, it's a 1 cross 1 matrix in star. Okay, and when you multiply with this you will get a m cross 1 vector. So u of n into d of n star, expectation of this, you will get P0. U of n minus 1 into dn star, expectation of this, you will get correlation at lag of minus 1 and so on. Okay. So in this case, in the first case, u of n and u of n, its Hermitian transpose, both are vectors. Okay. But when you find this P, this u of n is of course a vector, m dimensional vector, but this dn is a 1 cross a single element, you can say. Okay. So this is how you can solve this equation in terms of matrices. So the final solution we have in the Wiener-Hopf equation is your WO, optimum solution, is given by R inverse P. Okay. So we call these as Wiener-Hopf equations. R is a m cross n autocorrelation matrix. And this P, now these will be bold letters because these are vectors. Okay, R, and similarly P, it is M. This is M cross M matrix. This is M cross 1 vector, column vector, with elements P0, P minus 1 to P of minus M plus 1. Okay. So if any input sequence is given to you, if any input sequence un is given to you, and the filter length is given to you, that okay, we have m filter weights w0, w1 up to suppose wm minus 1 only. It may be 7 length, it may be 9, 11, 10, whatever it is. And if the desired response dn sequence is given to you, so you have to find the solution for the Wiener filter which minimizes the mean square error that is given by this equation. Okay. So what you have to simply do is you have to find this autocorrelation matrix of the input sequences, and then you have to find the cross correlation between the input and the desired response because both will be given to you. So based on those two matrices, if you solve these equations, you will get the filter weights which provides the minimum mean square error. Okay, this is what is Wiener filter.